Hello and welcome to the course Design Board Fields with Confidence. This is the first chapter of the sixth part where we will be talking about the TurboCollector from MuoviTech. Now the TurboCollector, it's an innovative type of heat exchanger. It's based on a circular smooth pipe, but now with fins inside. So when you move through this pipe, you will see that the fins rotate clockwise and counterclockwise. And the idea is that these fins induce turbulence at a lower flow rate, meaning that the heat transfer will increase in these areas. Now, in order to understand the importance of turbulence, I want to recap the Reynolds number and laminar and turbulent regimes we already discussed back in part 2 of this course. So if you recall, when we have a laminar flow rate, which is a low Reynolds number, so basically a low flow rate, let's say, what we have there is that all the droplets, they move parallel to each other, meaning that the droplets in the middle of the fluid, they have a hard time exchanging heat to the pipe wall and hence to the ground. However, if we increase the flow rate, the flow velocity will also increase, the Reynolds number will be bigger, and all the droplets, they will be mixing constantly. So it's quite easy for them to exchange heat with the pipe wall and also with the ground. Now, between this purely laminar and purely turbulent region, there is this transition zone that typically starts at around a Reynolds number of 2300. So for a regular smooth probe, at a Reynolds number of 2300, the fluid will become turbulent in some regions, laminar in the other, and when the flow rate increases even further, your Reynolds number increases more and more. Parts of your probe will actually be turbulent until you have a fully turbulent flow. So for this TurboCollector, it's really important that we model or that we know when the probe will be turbulent in the first place, but also how that will change the heat transfer and also the pressure drop. And in order to model that, we need something which is called computational fluid dynamics, or CFD in short. Now, modeling turbulence is really hard, but it's also one of the most important aspects in all of engineering. It's used in chemical plants to see how certain products interact with each other. It's used to simulate the shape of airplane wings and to calculate the drag on airplanes and fuel consumption and so forth. So it's a really important field in all of engineering, basically. So also for modeling the TurboCollector. And before we do that, I want to say a couple of words about how hard it is to actually calculate or model turbulence. Because there is no analytical solution to the Navier-Stokes equation that govern all of fluid behavior. There is actually a $1 million prize put to answering these questions. It's linked over in the textbook if you're interested in that. But basically, the problem with turbulence is that it occurs in small and in large time scales and also small and large spatial scales. And to understand that, if you look, for example, at the clouds, you will see turbulent behavior at basically kilometers. Clouds are very big structures. But if you zoom in, you will also see them on a very small scale, where it's very fast turbulence, whereas the big overall structures, let's say, of the cloud, they move at a different time scale. So it's really difficult because we have different scales in time and space. And there are currently 3 models available for modeling this, which is RANS, LAS, and DNS. So just to illustrate this, RANS, it's Reynolds averaged Navier-Stokes. It's basically averaging out all the turbulence. So it's not solving for the real turbulence behavior, and it's basically smoothing the behavior out. It's the fastest way of modeling turbulence, but as you can see, there is basically no detail in this. It's just a shade. So that's not suited for modeling these small fins inside of the probe. Then what's more and more becoming popular, it's what's called LES, large eddy simulation. And this is basically a trade-off between RANS and DNS, and it's solving turbulence, but only at the bigger time scales. So you can see already here in the examples that there are some turbulent shapes. It's not all smoothed out, but when you go to the edge of these bigger structures, you see that it's smoothed out. So there is no real turbulence at the smallest level here. So also the LES method, it's not suited for modeling the TurboCollector. What we actually need is something which is called DNS, which is just basically brute force direct numerical simulation of this Navier-Stokes equation. And what this will do is we will make a very, very fine grid alongside the pipe wall and inside the pipe as well, to model really the turbulence at these very small spatial and time scales. And as you can see in the examples here, you see all the regions, all the smaller turbulence already occurring. And this is exactly what we need to model the thermohydraulic behavior of this type of probes. Now, the modeling of this TurboCollector is actually based on the work of Nicholas Hittman in 2026. It's been published in the Journal of Fluid and Mass Transfer. And basically what it was a direct numerical simulation of both smooth pipes as a sort of reference and pipes with internal fins like the TurboCollector. And the philosophy was that they modeled these probes and then they started with a very high Reynolds number, so that we know the fluid is turbulence whatsoever. So based on that reference case, the Reynolds number was lowered each time until they reached a laminar regime, and then we know when the turbulence actually started, where this transition happens, and you can also calculate the effect on the friction factor, which has an effect on the pressure drop, but also the Nusselt number. And this then in turn has its effect on the convective heat transfer and the borehole thermal resistance. Now, this is the result from the paper for the smooth probe. And on top you have this very turbulent region, 3300, so it's very turbulent, which you can also see the fluid is beautifully mixed. And you also see this mixture happening, this turbulence happening. And you also see that at the pipe walls there is a very, very small boundary layer. And you see there a sharp gradient from this blue to this reddish color, but it's really small because in this turbulent region there is quite a lot of mixing and the heat gets mixed internally quite easily. When you go lower to 2050, we see that the flow rate is completely laminar. You clearly see these layers, the boundary layer is clearly visible here. The heat transfer is completely conductive. There is no mixing whatsoever, it's all parallel. So here we see that we go from turbulent to laminar regime. The same was done with pipes with internal fins, and here we have a slightly different story. So again at 3300 it's turbulent and we keep lowering it, and what you can see that around 2050, when the other pipe was clearly laminar, the TurboCollector is not. You see that in some regions it's laminar, but in other ones there is quite a lot of turbulence still, which is called the transient zone then. And you can go down all the way to 1700, where we again see these layers popping up and we have this laminar flow regime. But it's around 1700 that the transient zone actually starts. So instead of waiting to 2300 to get theoretical transfer between laminar and turbulent regimes, here it happens significantly sooner, between 1700 and 1800 Reynolds number. Now, based on these simulations, we can actually say something about the friction factor and the pressure drop, and also the Nusselt number, which tells us something about the heat transfer. Now, for the friction factor, we have this graph. The exact mathematical formulations are over in the textbook if you're interested, as well as the reference to the original paper. But basically what we see here is we have both the dotted blue line and the dotted green line, which are the classical solutions for smooth pipes, let's say. And then you have this red line, which is the correlation for this alternating DNS probe, which is the TurboCollector in this case. And as you can see, the friction factor, it deviates at around 1700, 1800 towards this turbulent regime. So the transition zone occurs not at 2300, but already way sooner. And also the Nusselt number changes. Now, the Nusselt number, we touched upon it briefly. It basically tells us something about how the convective heat transfer of the fluid relates to the conductive one. And basically you want a very high convective heat transfer, so we have a low borehole resistance, so we want a very high Nusselt number. And what you also can see here is that we have 3 different colors, so it's basically a map made in 2D. The correlation is a surface, and that's because we also have different Prandtl numbers. Now, without going too much in detail, Prandtl numbers also tell us something about the fluid's behavior. So depending on which type of antifreeze you will have a different Prandtl number. And here the green values are for Prandtl numbers 20. To put it in perspective, potassium carbonate is 25, and the red ones are for a Prandtl number of 75, which is around monopropylene glycol 33%. So basically all the type of antifreezes are somewhere in this red to green range. And also here you see that the standard laminar Nusselt number, which is 6 in this simulation, are 3.66 analytically. It deviates at not 2300 where you would expect it, but at 1700 it increases significantly, and then it converges to the Gnielinski correlations that are typically used to model turbulence in traditional smooth pipes. So also from the Nusselt number and hence the heat transfer perspective, the turbo effect is clearly visible since it lowers the threshold to become turbulent, or at least transient. Now let us see how these 2 correlations, how they translate into actually the borehole effective thermal resistance as well as the friction factor. And to recap or to revisit what we talked about in the last part, we have here the same graph for a probe of 100 meters borehole depth in a borehole of 140 millimeters, a grout of 1.5 watt per meter Kelvin, and monopropylene glycol 25 volume percent, 5 degrees Celsius. We see here our single and our double U-tube, but we also now see the single and the double TurboCollector. All of them DN32, BN16. And what you can see here is that the turbo effect is clearly visible because the turbulence, or the drop-off towards this transient zone, it occurs at a lower flow rate, the lower Reynolds number for this TurboCollector, both for the single and the double one. But what is interesting is when we were talking last time about, well, there is a range in which the single outperforms the double U. When you compare the W smooth with a single TurboCollector, this range is significantly bigger, between 0.18 and 0.45, let's say, instead of 0.25 to 0.45. So it increases the range in which a single probe can be more beneficial than a double one. What is also interesting is that instead of comparing probes with the same diameter, what we also did last time is saying, okay, let's compare it with a smooth DN40 pipe, single one. And what we saw there is that due to the fact that turbulence started later, you need a higher flow rate for this bigger diameter to also become turbulent, that the range in which a single DN40 is better than the double DN32 is quite small. It's between 0.3 and 0.45 liters per second. But the difference is actually higher. So it's in a shorter flow range, actually a significantly better solution. When you compare that to the single TurboCollector DN40, again the same effect happens. The turbulence starts sooner, so the range in which our single DN40 outperforms the double DN32 now has become bigger due to this turbo effect. So that's also clearly visible here. Now if we then take a look at the other side of the picture, the pressure drop, we see here again the single and the double. And what we also see is that the pressure drop in the TurboCollector, single and double, it's more or less identical than the smooth probes. It's a little bit higher due to the fact that you have these fins, but it's barely noticeable on this scale. What is noticeable, however, is that the increase in pressure drop, it occurs at a lower flow rate. And that's basically the price you pay for having better turbulence. Right? The fact that you have turbulence, better heat transfer, yeah, you have to pay for that with a higher pressure drop. So that's why you see this deviation at 0.35 liters per second for the W and let's say 0.16 or something like that liters per second for the single. If we now add again the dm40 to this equation, you see that the pressure drop is significantly lower, as we discussed already last time, for this single dm4 than for the single dm32, due to the fact that we now have a larger diameter. And also here, the single smooth and the single turbo collector behave more or less the same, except for this region in which the turbo collector is already turbulent, but the other probe is not. And then you also see that the double smooth pipe, it has a slightly lower pressure drop, especially in this turbulent region, and in the laminar region, both the single and the smooth and turbo collector have the better pressure drop. So this was what I wanted to say about the turbo collector, how it was modeled, what computational fluid dynamics is, how we model turbulence in these type of probes, and also show you what the benefits are when talking about the effective boil-down resistance as well as the pressure drop. In the next chapter, we will cover its younger cousin, the MuoviEllipse.